Okay. Okay, looks like, okay, still waiting on one, but we'll go ahead and get started. All right. Okay, so I'm going to talk about functional groups today. In the video that I gave on Friday, I talked about Lewis structures, which represent the order in which atoms are connected. A functional group is a group of atoms that occurs with great regularity throughout organic compounds. And this actually is something that's very essential for you to learn. It's almost like learning to read, and to learn to read, you have to know the alphabet, so functional groups are a lot like the alphabet. Can you hear me in the back? Seems like I'm kind of muffled, but okay. I'll try to talk loud and try not to turn my back. Functional groups. Okay, functional groups can be organized according to what elements or what other elements are present. We'll start out, this is not a functional group, but a general class, and that is the hydrocarbons. And hydrocarbons contain only carbon and hydrogen. This is a general class. Okay, there are 4 functional groups within the hydrocarbons. We have what are called the alkanes. And these contain only single bonds. And an example would be this, which is propane. Okay, next we have alkenes. Now, alkenes will contain one or more CC double bonds. And knowing the functional group not only allows us to name the compounds systematically, but also it serves as a basis for predicting their properties and their reactions. And so an example would be ethylene. Okay. The third class of hydrocarbons, and these are functional groups here, are the alkynes. Okay, alkynes will have one or more carbon-to-carbon triple bonds. Okay, and the simplest example is this one. It's acetylene, commonly called acetylene. Systematically, it's called ethyne. E-T-H-Y-N-E. Ethyne. And then the fourth class is what we call arenes or aromatics. We'll spend a whole chapter defining what aromatic compounds are, but for the moment, we'll say that aromatics are going to be compounds that are like benzene. Right, in benzene, okay, this is the structure of benzene. Okay, and immediately the question arises, well, why isn't benzene an alkene? It doesn't react like alkenes. It has its own set of reactions. Okay, so these are functional groups which, as the name implies, they react in a certain way. Benzene and related compounds react very differently from alkenes. Okay, I'm going to go ahead and erase this so I'll have some more space. Okay, those of you on Zoom, can you hear me okay?
Yeah, I can hear you.
Okay,
Yeah, you're
good.
Thanks. Okay. Okay, then we have what are called alkyl halides. Or also called haloalkanes. Remember, alkanes are hydrocarbons. They have only single bonds. But if we replace some of those hydrogens with halogens, then we've got a haloalkane. Okay, so I've replaced one of the hydrogens, in this case with the chlorine. The halogens are fluorine, chlorine, bromine, and iodine. Okay, we start with an alkane, okay, which is that's a hydrocarbon that has only carbon and hydrogen. And then we replace one or more of those hydrogens with halogens. Okay, in this case, I've replaced a hydrogen with chlorine. The halogens consist of fluorine, chlorine, bromine, and iodine. alkyl halides are considerably more reactive than alkanes, and their reactions are going to be very different. Okay, so replacing hydrogen with a halogen changes the chemical properties significantly. Okay, then we have several functional groups that contain oxygen. We have, first of all, the alcohols. And at this point, I'm going to introduce the symbol R. Okay, so R, OH. R is some unspecified carbon group. Okay, could be one carbon or two carbon or some number of carbons. Okay, so this is ethanol. And then if I replace one of those hydrogens with an OH, now I have an alcohol. And here's one I just used this morning. This is isopropyl alcohol or rubbing alcohol, used as a disinfectant. Okay, so the R, again, is some unspecified carbon group. Okay, alcohols have similar reactions, and the reactions will occur either at or in the vicinity of that alcohol functional group. All right, next we have the ethers. And ethers have the general formula R, O, R prime. Okay, the reason that I indicated R prime is that the two R groups don't necessarily have to be the same thing. Right, so this is an example. In this case, both groups are the same. This is ethyl ether, or this is what is commonly referred to as just ether. It's an important solvent used for extracting lipids from plant and animal materials. It used to be used as an inhalation anesthetic. Okay, so here's another example of an ether. Oops. Here's another example of an unsymmetric ether, where R and R prime are different. these are going to react, since they're both ethers, they're going to react very similarly. Okay, so alcohols are R, and then O, and then H. An ether has the oxygen connected to two carbons, rather than a carbon on one side and a hydrogen on the other. Okay, so that's an ether. Okay. Then we have several functional groups that contain a carbon-oxygen double bond. This is called a carbonyl. The carbonyl is not a functional group. But it is a part of several functional groups. Okay, it itself is not a functional group. Okay, so functional groups containing the carbonyl. Okay, we have this type of arrangement where we have a hydrogen on one or both sides. This would be an R group. This is called an aldehyde. And this one, as an example, is formaldehyde. Okay. But R could be 1 carbon, 2 carbons, 10 carbons. Okay, it's some unspecified hydrocarbon group. The reactivity is going to occur right around the aldehyde group. Okay, so that's an aldehyde. If we have carbons on both sides, like this is a ketone. Okay, note the spelling, Ketone, it's not ketone. Okay, there's no Y in ketone. This is an example of the difference here between a ketone and an aldehyde is this doesn't have a hydrogen attached directly to the carbonyl carbon. And this is commonly called acetone. It's, acetone is a useful solvent. You'll probably be using acetone not only in your reactions, but also as a wash solvent. This is commonly called acetone. General formula for a ketone is R, CO double bond, R prime. Okay, so just like the ethers, okay, even though I have both groups the same here, I can have an unsymmetric ketone. I'm going to go ahead and erase this. All right, some of the other functional groups that contain the carbonyl include this one. Right, this is called a carboxylic acid. Carboxylic acid gets confused a lot with aldehydes. This has an extra oxygen. Okay, the aldehyde lacks this oxygen. And an example would be acetic acid. Acetic acid is the principal component of vinegar. All right, if I replace that hydrogen with some carbon group, okay, and again, I'll call this R prime. To indicate that the two R groups don't necessarily have to be the same. This is called an ester. The difference between an ether and an ester. Okay, the ester has the carbonyl group. The ether does not. Okay, these get confused a lot. Okay, so this has the extra carbonyl group. Okay, if we replace this one oxygen with a chlorine, this is called an acid chloride or acyl chloride. Okay, and because of the presence of the carbonyl group next to the chlorine, this will react very differently from alkyl chloride or alkyl halides. Okay, I'm going to go ahead and erase these because I've got some more to include. There's one more that contains a carbonyl group. Okay, this is called an amide. And nitrogen forms 3 bonds. These bonds can either be to hydrogens or to carbons. Okay, so these can both be hydrogens, or this could be a hydrogen, and this could be some carbon group. Okay, so that's an amide. Okay, next we'll transition. This is a place where we can transition to functional groups that contain nitrogen. This is the first one. The second one is an amine. The difference between the amide and the amide has the carbonyl group right next to the nitrogen. The amine doesn't. Okay, so examples of amines. Okay, so here are a couple of examples of amines. Okay, you start with ammonia, which is NH3, and then you replace the hydrogens on ammonia, and you get an amine. Okay, you can replace one, two, or all three of those hydrogens. All right, and then the third functional group containing a nitrogen is this one. It is the CN triple bond. And this is a nitrile. Okay, and then the last set of functional groups are those that contain sulfur. Okay, I'll use the term from time to time called heteroatom. Okay, if I say a heteroatom, that's something other than carbon or hydrogen. Okay, most commonly it's oxygen or nitrogen or sulfur. Those are the most common heteroatoms. You can also have things like phosphorus occurs less commonly, but organophosphorus compounds can be important as well. Okay, but something other than carbon and hydrogen. Okay, functional groups containing sulfur. Okay, sulfur and oxygen are in the same family of the periodic table. Sulfur is right below oxygen, so we would expect sulfur to bond similarly to oxygen. Normally forms two bonds. This is called a thiol. The older term, I'll just mention this. The older term was mercaptan. Okay, so if you go back, if you happen to be reading an article from 40 or 50 years ago, may refer to mercaptans instead of thiols. And actually, the term mercaptan is still used in the oil and gas industry. Okay, if we have RS, R prime, okay, this is called either a sulfide or a thioether. Okay, note the analogy to an ether. Remember, an ether was RO, R prime. Okay, if we replace that oxygen with a sulfur, we have a thioether or a sulfide. And then the third one is this one. This is called a disulfide. And a disulfide is an important feature of protein structure. Okay, for example, the main protein in in your hair is keratin, and keratin has lots of disulfide bonds holding it together. Okay, we'll have more to say about that when we get to that particular chapter. Okay, so these are the functional groups. Okay, make sure that you learn those. This is a very important basis for organic chemistry. Okay, all of well, pretty much, I won't say all of it. Most of the chapters in our textbook are organized around functional groups. Okay, so again, knowing functional groups allows us to predict their reactivity and also to be able to name them systematically. Okay, on the first day of class, I said that there were about 10 million organic compounds that are known. Okay, it's impossible to go and individually assign names to those, but we'll learn about a systematic method of naming compounds. Okay, what I want to go over next is a shorthand, a couple of shorthand methods of drawing structures. Okay, this is what's called a molecular formula, C4H10. But that doesn't tell us anything about the structure, because it turns out there are two possible ways to draw Lewis structures for C4H10. Okay, we can draw this one. We can also draw this one. Okay, they're both C4H10. They are different compounds. They have different properties, different melting points, different boiling points, for example. So these are Lewis structures. Drawing out Lewis structures, especially for larger molecules, can get very tedious to draw every single bond. And so there are some shorthand ways which still preserve the structural information. Okay, for example, we can write this as CH3, CH2, CH2, CH3. Okay, even though we write it as CH3, CH2, okay, note that the hydrogens are, it's understood the hydrogens are not between the carbons. Okay, this represents that. And we can write this as a condensed molecular formula. Okay, and we still have all the structural information. Okay, we can go even further in condensing the structure. For example, this one. Okay, since we're repeating the CH2, we can put that in parentheses with a subscript 2. Okay, and then this one could be written as CH3 in parentheses with a subscript 3. Okay, the CH3s, it's understood that the CH3s are not connected to each other. So CH3 is repeated 3 times. Okay, again, this is another straight change. We've got 1, 2, 3, 4. We could write this as CH3 parentheses, CH2 in parentheses subscript 4, and then CH3. So this tells us that we're repeating. We've got 4 of those CH2 groups. Okay, so anything in parentheses is repeated. Okay, so this would be the formula for bananas. All right, we can go even further in simplifying structures using what's called a line angle formula. All right, so because a carbon with all single bonds has a tetrahedral geometry, this 5-carbon chain is actually not a straight chain, but it actually zigzags. And what we can do is we can represent each one of those carbon-carbon bonds as a line segment. Okay, so we would write it like this. I'm going to redraw this. Okay, so at the end of every line segment is a carbon atom. Okay. So it's understood that there are carbon atoms here. And since carbon forms 4 bonds, okay, it's also understood that the bonds that are not shown would be to hydrogens. Okay, so for this carbon, there are 2 bonds shown, so it is implied that there are 2 hydrogens. For this carbon, 1 bond is shown, so it's implied that the other 3 are to hydrogen. going to go ahead and erase this. Okay, we can even do branch chains. Okay, so each one of these line segments represents a carbon-carbon bond. Okay, so how many hydrogens would this one have? Two, right. How about this one? One. How about this one? None, right. It already has 4 bonds. What about this one? 3, right. Okay. Okay, so carbon has 4 bonds. The bonds that are not shown, it's understood, it's implied that they are 2 hydrogens. Okay. One last comment about line angle formulas. Okay, double bonds, triple bonds have to be shown explicitly. And again, since there's 3 bonds here, it's understood that there is 1 hydrogen here. Also, heteroatoms, okay, most commonly oxygen, nitrogen, sulfur, okay, those also need to be shown. And hydrogens on heteroatoms. So if we have an OH down here, okay, this hydrogen has to be shown. All right, and we're out of time, so I'm going to go ahead and end there.